And now it should read the SD card and put it in memory. Let's power it on. Let's see if it actually failed. Nope, there it is. It worked. Today I want to talk about my message blade, what it is, how it came to be, and more importantly, how you can make one for yourself. So it all started with this simple LED matrix, 8x8, single color, and I kind of wanted to use it for a product, or project in this case, and I thought, well, it would be great for a subscriber counter. I mean, I only need one display, seeing how my channel is going, so that would be a great idea. But then I thought, like, you can't do much more with these. So the idea was born to create a message display, and yeah, that sounded like a fun product. So the first problem I had to solve is how many of these LEDs do I want to use, these matrices, and I decided on 10, and that will be the basis for my design. And here you can see the finished prototype, and obviously 10 was a good amount, so I ended up with 12, as you do. I mean, bigger is better, right? And the other problem was, what driver chip am I going to use? And I ended up using the very popular MAX 7290 IC, which is often used to drive and multiplex 7-segment displays, but it works perfectly for these as well. So that was my design choice. I've got my module, I've got my driver chip. Now I had to think about the interface. Now I wanted to have scrolling text and animations and an easy way to input it. So I did not want to hard code it, and I didn't want to create a keypad. That would be far too expensive. And I have seen solutions where people have just 2 input keys, but they have to double tap or multi-click to get a single letter, and then tap and then another letter, and by the time you've input a word, you've lost your will to live, let alone getting a sentence in. So that was not an option. But I still wanted only 2 buttons for the interface, so I settled on a card reader. I'm like, oh, that's a good idea. Just use an SD card reader. And these card readers are dirt cheap because they do not have any active components. All they do is basically translate or these pins to a connector to the PCB. So there's no smarts in it. The only smarts they have, if you can call it smarts, they have a little switch that can detect if the SD card is inserted. That's all. So they're dirt cheap. So I'm like, yeah, that's a good idea. I'm gonna somehow put my message on the SD card, read it in, store it, and then that will be it. So that was the basis of the idea. Now let me show you another prototype so you can see how it's actually built. So I removed 2 of these displays, and you can see I've got the driver chip underneath each display, and I put headers on there so I can take a defective display off and I can put on a different color, because these come in different colors, so that's cool. Easily said than done though, because I still had a router issue, but that became apparent later. But the other problem I had was the chips themselves. They are insanely expensive. And when I say insanely expensive, they're about $12 each. But I need 12 of them, so even 10 would be $120, but 12, no, that's too expensive. So I had to look for a different source. And lo and behold, I found them online very, very cheap. And when I say cheap, very cheap. Instead of $12 each, there would be 80 cents each or less. But I thought, like, nah, that doesn't sound right. They're obviously illegal duplicate chips, reverse engineered, so I didn't want to buy those. And I found a third option, and in Australia we have a very popular electronic store that sold these modules and the chip bundled. So you had the module, a PCB, and the MAX 2790 for, I don't know, $4 or something like that. And I'm like, oh, that's great. I'm just going to buy these modules. That will give me the displays and the chip for next to nothing. So that's what I end up doing. Unfortunately, yes, you guessed it, they used the illegal counterfeit chips as well. So yeah, didn't end up helping me. What does it do? What is the issue with these chips? Well, they kind of work the way they should, but every now and then they glitch. In this case, if I leave this blade on running for more than an hour, half an hour, some of the displays just get garbled and I need to reset it. So I included the reset button. And these two, A and B, are the menu buttons. So, and there's really nothing I can do about it. All these chips are daisy chained. And you got the clock and the actual data out. And for some reason, after a while, the data or the clock just gets out of sync and you have to reset the display. So I found a way to do it in software, just put on a timer and every, I don't know, 10 minutes reset in such a way that you wouldn't see it. So it would wait until a message has displayed, quickly reset and then resume. But yeah, it's not ideal. But for my prototype, it's more than I needed. I also wanted to keep it very flat. As you can see, that worked. The only downside is I had to order these PCBs and they're quite expensive because of their size. But hey, you get 5 of them, so hence I've made 5 prototypes. Now let's go into, before we go into the software, let's demonstrate it. Let's show how this works. So I actually prepared an SD card, and this has a few lines of messages on there with some numbers in my own format that allows me to just display text, animations, sprites, etc. So the way you input it is put the SD card in, click it in, it should detect it. Now, mind you, only use old SD cards or low value ones. This is an 8 gigabyte. 32 gigabyte or high speeds don't work. Now, there's nothing to do with the card reader. It's all to do with the library and the microcontroller. So old SD cards work, modern ones won't. So you just gotta experiment. So from memory, and it's been a while, you can see the date code is week 43, year 2020. So trying to memorize, trying to recall how it works. I think I had to hold the A button and then power it on, and that would erase the memory and read the SD card. So let's try that. Yes, memory erased. Good. And now it should read the SD card and put it in memory. It says initialization failed. Let's power it on. Let's see if it actually failed. Oh, there it is. It worked. Brilliant. All right. Let's go through all the options. So you have scrolling, animations, as you can see. Put in a couple of animations. And then it will just repeat over and over. So let's power it off. Let's remove the SD card. Let's see if it still works. Let's see if it's persistent. And it is. Now here you can see an LED matrix diagram. Now I could not find a datasheet for the life of me on the internet. So I had to figure it out pin by pin. And as you can see, the pinout is far from logical. It seems to be a bit random. I've drawn this in Visio, by the way, if people are wondering what I've used. I use Visio for just about anything for many, many years. I just find it easy to use to make diagrams like this. Anyhow, as you can see, the rows are the cathodes of the LEDs and the columns are the anodes. And a very important detail is the matrix is keyed. There's a little notch on the side. I did not put that in the drawing. I should actually do that. That tells you how to orient it. And next to it, you can see the driver chip I used, the 7219. And I think it drives it with 800 Hertz. But this is a very important schematics if you ever want to play with these displays. So let's have a look at these schematics. Here you can see the heart of the message plate, the microcontroller. And I've used a 1284 8-bit microcontroller. I used to do everything with the trusty Atmega 328P, but I just needed more memory, more RAM, more flash. So I just choose a bigger chip. Now this is a very old design, guys, 2020. Normally I would have used a SEM21 or ESP32, but for this design an 8-bit processor is more than sufficient. Now it's a very simple setup. You can see I'm using a resonator. You don't need a crystal, and a reset functionality. I always include this, but it was very useful for this design because of these glitchy chips, but always include a reset. And the only interface I use are these two buttons. Now you can see they're directly connected to ground, so they're active low. That means I'm using internal pull-up resistors to actually make sure they're in a stable state when they're not pressed. All right, let's have a look at the power supply. Now the project is 5-volt powered by the USB port, but I do need 3.3 for just the card reader. So I'm using the trusty low dropout AP2112 to turn 5-volt to 3.3 volt. And like I said, it's only used in the card reader. Now, if we have a closer look at the card reader, because it's 3.3 volt and we're using SPI signals, I got to make sure that the input are actually level shifted. So I'm using a 7450 4050 to do that. It's a high to low level shifter. So I only care about the input signals, the clock, the MOSI, and the CD or chip select. The outputs, I don't really care. Now this particular symbol is the card reader. It's just a connector. So I'm connecting all the shield pins, and I don't really do a lot special with it. I don't even think I'm using the detector switch. Oh, I actually do use the card detection. So the card detection is kind of an inbuilt switch that tells you if the card is inserted. So we have a look at the microcontroller. I'm actually using that as well. As the microcontroller is concerned, it only uses the SPI bus and all the other ports aren't used. So kind of overkill using a 2012-84, but meh, I've had them available and they're not expensive. Now as for the driver, I'm using the driver chip and the matrix, and they're very simply connected. I just needed the load, chip select, and the clock, and they're kind of in parallel. And then the MOSI, master out slave in signal, goes into the input and it daisy changes it via its output to the next chip input and so forth. So it goes all the way down to the end to DA1, and it goes into DA1 here, the next chip. So they're all daisy chained. So it's very simple. Here you can see a single LED matrix that has its columns and rows directly connected to the driver chip. Now the driver chip will take care of all the multiplexing. So the only thing you really need is get in the SPI signals here, and you can use the iSet to change the display brightness with a static resistor. I'm using 10K, and everything else is done in the chip. So it's a very simple design. Now let's have a look at the PCB. The PCB was a bit challenging because it's not easy to route. There's a lot of pins on display, so I've decided to use obviously a 2-layer design. The matrix LEDs, because of their build, actually have a little bit of empty space, so I put the driver chip directly underneath the LED matrix, and the chip and the controller I put at the bottom. So let's show you the top. I'll just remove the traces altogether, makes it a bit easier to see. So we have the microcontroller, go away. Okay, so we have the microcontroller here, very close to the USB port. And the only thing we have is a unpopulated in-serial programmer, because I use pogo pins to program it. I mentioned that earlier. And we have 3 buttons, our reset and our A and B. So this comprises the menus. It's very simple. Now this is a very long PCB. So at the very end, we have our card reader and our level shifter. And because there are very long traces, let me switch them back on. Let's remove that one so we can see the power traces. There will be a voltage drop. So I used big traces for the 5-volt to go all the way down to the end, and then very close to the card reader I'm converting it to 3.3 volt, so there's not a lot of power loss. So everything is done on the end here. So it's a very simple design. Let's have a look at the code. I I don't really want to go too much in depth and explain each and every line. The only thing I want to show you guys a very useful library, and that's the Prorola library. So that's basically a library I discovered to drive matrix LEDs, and it's got a ton of built-in functionality, so it's very easy to use. The other important library I'm using is the MAX7290 library for the driver chip, and that's it. And obviously the SPI interface, the SD library, and the EEPROM library to store the actual messages. And that's basically it. Now the hard part was to figure out my own protocol, like how do I store the text. So this is the SD message format I've designed. It starts out with a text you want to display. That is a maximum of 20 characters, followed by a few numbers, and it ends with an asterisk, and this tells the software that it's finished the line and goes to the next line. Now let's go through these numbers one by one. So the first I explained is text, 20 characters max. The next number gives you 3 options of text positioning. So this means where does the text end up after the animation. So it could either be in the center, left or right. And then we have the animation speed, aka how fast is the text going to move. And again, we have 5 options, 0 to 4. And this is the speed in milliseconds. Then when the text is animated, how long do you want to hold it in place? A max of 8 seconds, all the way down to 0. And then we've got the 2 major important bits, the animation in and the animation out. Now 0 to 19 are all pre-programmed options in the Prorola library. And we've got very obvious names, scroll up, scroll down, etc. And the last one I've added in is if you don't want to use text animation, you want to use a sprite, you can use this option 20. So this is, the next one is how do you animate the text in, how do you animate the text out? And if you want to use a sprite at the end, what sprite? So I've got 2 types of Pac-Man, a heart, a wave, 2 arrows, a walker, that's an AT-AT, Star Wars, an invader, and I've created an enterprise. But you can create many more effects, just, yeah, you can add it in the code. And then there's 2 modes on the message blade. The default mode will read this line by line, put it in EEPROM, and then it will just run it indefinitely, top to bottom. But you can also set it to a B mode with the B button, and then it will just do 1 line and then stop until you press the button. We'll go to the next and the next and the next. And then when it hits the end, it will go back to the first message. And that option is handy if you don't want to scroll through all the messages, but actually want to display a single message, like I'm recording or I'm on lunch break, so you can just scroll through several messages and just display that. And that's basically it. I hope this will give you some inspiration of building your own message blade. If you're interested, I have a bundle, a zip that gives you all the Gerber files, all the code, all the diagrams, all the PDFs, everything you need to build it, all bundled in a zip, and that will be available on my website, and you can just buy it for $2 if you're interested. And that will help me making more videos. Now, on hindsight, what would I have done different with this project? I think if I were to recreate it now, I would probably go for an RGB matrix, maybe, or just use individual chips. And I'd probably go for an ESP32. And the reason is I kinda don't want to use a card reader anymore, it's just too cumbersome. I'll probably go and use the ESP32 Now protocol to remote in texts, and that also gives me the capability of connecting it to the internet for local time or stock messages or whatnot. So you can make it a bit more dynamic. But all in all, it's a very fun product, a very fun project. And it taught me a lot about display drivers and trying to read code or read information out of an SD card via code, etc. So it's a very cool project. So I hope you enjoy it. And if you have any more ideas of what I could do next with this project, please let me know in the comments, and I'll see you next time.